This is a video to go over lesson 5.1, which is on areas and distances. So for the first part of this course, chapters 2, 3, and 4, we've been really focusing on finding slopes and slopes of tangent lines and derivatives. The second half of the course, so for chapters 5 and 6, we're going to be looking at areas under curves. So today we're just going to start by estimating the area under the curve, and then in future lessons we're going to be able to calculate the areas under curves exactly. Okay, so let's look at our example here. I'm just going to zoom in so we have some space to write. Here is a curve y equals x squared. So when I say area under the curve, what I mean is this area shown here in yellow. It's the area between the function and the x-axis. So this is actually exactly 1 over 3. So later in the unit, like I mentioned, you're going to be able to calculate that exactly. But today we're just going to focus on estimating it. So really the best way to estimate this area here, because we don't have a formula for estimating the shapes with strange shapes like this. We really only have formulas for circles, triangles, rectangles, right? So we're going to split this up into some rectangles and calculate the area of all the rectangles, and that'll give us at least an estimate for the area. So let's look here. We've split this up into 8 rectangles, okay? Since it's 8 rectangles, the width of every rectangle is 1/8, because 1 divided by 8 is 1 over 8. And the height of every rectangle depends on the height of the curve at that particular point. So for example, let's just take this rectangle here. So that's 1/8, 2/8, 3/8. That height would be, so this is 3 over 8. So the height would be the height of the curve at x equals 3 over 8. Well, we have the formula for the y values on this curve. So the height there would be 3 over 8 squared, which is 9 over 64. Okay, so you can get the height of all of those rectangles that way. So if we were going to write down a little formula for the area here, it would be 1 over 8. So we'd add up the width times the height. So the first one would be at 0 squared, because the height of that first rectangle, well, you can't even see it because it's 0. The second rectangle would be 1 over 8 squared, plus 1 over 8 times the third rectangle would be 2 over 8 squared, all the way to the end. The last rectangle is at x equals 7 over 8, so it'd be 1 over 8 times 7 over 8 squared. Okay, so that's an expression there for the area under that curve. If you type it all into your calculator, I'm not going to ask you to do that, but if you did, you'd get about 0.273. So remember I said the exact area is 0.3 repeating, so 1/3. So it's a little bit less. That's because you've got these white spaces here. And we call this estimate, we have a special name for it, because we're using the left endpoints, meaning each triangle or each rectangle, when you draw it, see the left side comes and touches the curve. So the leftmost point on the rectangle is what's hitting the curve. So we call this estimate L for left, and then 8 because there's 8 rectangles. So L50 would be the left endpoints with 50 rectangles, okay? You can also write this, yeah, okay, so we'll do that. And then you can also use the right endpoints as well, which is shown on the next part, in part B, and we call that R8. R standing for right, and then 8 because there's 8 rectangles. They have the same width every time. So the width of each of these is 1/8, except now instead of the left endpoints touching for each rectangle, the right endpoints touch. So I'll just pick one to draw over an example. So here's a rectangle, see the right side is touching. So the different heights are the heights at each of these 8 x values, whereas over here, the heights were from these 8 x values. Okay, so it's almost the same calculation, except instead of starting with 0 squared, we're going to start with 1/8 squared. 1/8 squared plus 2/8 squared. And the last x value is 1, so 1 squared. A dot, dot, dot you can use if it's the same thing over and over, and you just fill in the blanks there. Okay, good. So that's going to give you an answer that's a little bit greater than 1/3, which is 0.398. Okay, so that's just a little bit of background and notation. On the backside, we're going to do an actual example where we calculate or estimate the area. But let's see, if we were interested in getting a better estimate, what could we do? Let's look down below here. We could increase the number of rectangles, right? So this is what L10 looks like. This is what L30 looks like. And this is what L50 looks like. So as you increase the number of rectangles, your area estimate's getting better and better. You're reducing that amount of white space that you're missing there. So this one turns out to be 0.3234. We're getting really close to the exact answer, which is 0.3 repeating. Okay, let's just go over a little bit more notation here. This is a little general formula for Rn. I'll write down the one for Ln in a second. So remember, for Rn, there we go. We're using the right side of the rectangle to touch the curve. Okay. N denotes how many rectangles you have. This little piece here is your width. That's delta x. That means change in x, so the width of every rectangle. And f at x1, f at x2, f at x3, f all the way to f of xn, that's always the height of each rectangle, right? So, or length. So length times width, right, is the area of a rectangle. So you have first rectangle, second rectangle, third rectangle, all the way to the last one. If you were doing Ln, you would just start 1 over. So you'd do f at x0 delta x plus f at x1 delta x plus f at xn minus 1 delta x. Okay, and the exact area under the curve is going to be the limit as n goes to infinity of Rn, or the limit as n goes to infinity of Ln. So the limit as you get, so an infinite number of rectangles would give you the exact area under that curve. Okay, so let's do an actual example now that we've got all the notation out of the way. Let's say we're looking at this curve e to the x, and we want to know what the area is under that curve. So we are going to draw some rectangles to do that. So let's say we want to, so first A, we're writing an expression for the area under the curve as a limit. So B, you can just write, we're not gonna do a complicated, you can make this more specific for the actual curve, but we'll just write limit as n goes to infinity of Rn, or limit as n goes to infinity of Ln. That'll be enough for us for now. Now we're going to do R4, L4, and then we'll introduce a new one, which is M4. So let's focus on R4 to start. Okay, so for R4, so notice I'm going to split this into 4 different regions there, right? So delta x is going to be 0.5. The width of each rectangle will be 0.5, right? And we're going to be drawing our rectangles. So for R4, the way I like to draw my rectangles is from the right side. That helps me remember where the rectangle should go. So I'm starting on the right side, and I'll draw my rectangle down like this. Okay, and then I'll do the next one like this, the next one like this, and the next one like this. So notice I don't even use that leftmost point, okay? So the area, so R4 is going to be, so the height of the first rectangle is the height of the curve at 0.5. So it would be e to the 0.5, and the width is 0.5. The height of the second one is e to the power of 1. E to to the power of 1, and then the width of every rectangle is 0.5, so we'll just write 0.5. The next one is e to the 1.5. The width is 0.5. And the last one, the height is e to the power of 2. Okay, if you want to type this in your calculator, I recommend pulling out the 0.5 and only typing that once. It's much easier to do 0.5 and then just type in these e to the 1.5 plus e squared. That's almost half the amount of typing in your calculator that you need to do just by factoring out the 0.5 there. Okay, so I recommend actually doing this one just because you might not be used to using e in your calculator. It's good practice. Once you type that in, do a little squiggly line for, oh, I guess it is exactly equal to R4, so we'll do that. 8.119. Oh, I did the squiggly line because it is a decimal that goes on forever. Yeah, it's an irrational number. Okay, so I kept 3 decimal places. So the area is approximately 8, but we know this is an overestimate because see, my rectangles go over the curve. So let's see what L4 is. So for L4, I like to start my rectangles from the left. That way I know where to draw them. So here's the leftmost point, over and down, left, over and down, over and down, and over and down. Notice I did not use this last point here. Okay, so the width of every rectangle is 0.5. So I'm just going to use this little trick where you factor that out. So that's the width of every rectangle, and then I'll just write down the height. So the height of the first rectangle is e to the 0, which is just 1. The second one is e to the 0.5. Third one is e to the power of 1. And last one is e to the power of 1.5. And if you type that in, you get 4.924, which obviously that's an underestimate because these there's a lot of space left over once we do this area. So the real area is somewhere between 4.9 and 8.119. I'm just going to color these in so you can see. Okay, so let's get a better estimate. The other way to get a better estimate if you don't want to do more rectangles is to use M4. So here's M4. So here's our intervals. What you want to do is take the middle point in each interval. So middle point, middle point, middle point, middle point. And you want to draw your rectangles from there. So you draw it across from there. So take the middle point in this rectangle, there we go, the middle point in this interval, and the middle point in that interval. Okay, so that's the area we're going to calculate. This is better because, especially for curves that look like this, because you get a little bit of an overestimate on one part, but then a little bit under on the next. So this is a much more accurate estimate in this scenario. So M4 is going to be, so the width of every rectangle is still 0.5, but this time the heights are at different x values, right? This was 0.25, this is 0.75, this is 1.25, and this is 1.75. Okay, so e to the 0.25 plus e to the 0.75 plus e to the 1.25 plus e to the 1.75. So you type that all in your calculator, and you get something like 6.323. So that's a much more accurate estimate there. Okay, so not too much of an assignment today, so really short first lesson for chapter 5. There is one question I want you to do from 5.2 though, so just be aware of that. Okay, so that is it for 5.1.